So we will now turn our attention to a device having two top contacts, and therefore we can no longer use the mount as an electrical contact plane. We will therefore require the second probe, and by virtue of requiring to connect between the two, we should move the first probe towards the rear. In that manner, we can move the link between the first probe and the mount to the mounting point on the second probe. The second probe is fitted with a shorting stub to short the center pin of the BNC, which is connected to the probe to the shield of the BNC. We should position the device we wish to test under the monochromatic probe and proceed to make electrical connection, lowering the probe onto the electrode, clamping in place and clamping the magnetic base in place. And similarly here with the first probe, clamp down in place and clamp the magnetic base in place. So we are therefore ready to measure the spectral responsivity of this device. I've turned off the vacuum, and I've also turned off the temperature control of the VCT20, since this device is on a isolating material. There will be no electrical connections, of course, and no thermal connection either.
So we will now consider a sample with both top contacts. We will remove the silicon device from the temperature control vacuum mount and replace it with this new device. Firstly, of course, we should position the device with respect to the monochromatic probe, and to that end we will, rather than go through the motorized stage utility, we can use the go to wavelength function in the icon bar. This go to wavelength function allows you to set the monochromator to transmit a previously defined wavelength. Alternatively, one can go to scan signal setup or follow the signal setup shortcut to input a target wavelength. So for example, 555 nanometers in the green, we can set quick wavelength to define to which wavelength we go by hitting this button. Now we have light in the sample, we can proceed to make electrical contact and adjust the position. Whilst we have already calibrated the system over the range 300 to 1200 nanometers, in the specific case here of an amorphous silicon device, we need only measure up to around 800 nanometers, so we will change accordingly the end wavelength. Now, again, as opposed to the previous sample, a production grade monocrystalline silicon sample, the amorphous silicon sample here is of research grade, and one does question how the sample will deal with the one-sun bias. So in the first instance, I will perform a scan with no light bias applied to see what response we get. Here, the only thing that can go wrong is if we have poor electrical contact, which we will see directly if we have a good responsivity measurement or not. So I will save this result as the amorphous silicon in the dark, so without any light bias. And we can see that the result is noise-free, a nice spectral responsivity measurement. The question is whether, if we did the measurement with light bias, the sample would take the heat. I would suggest that rather than performing a measurement with one sun, to reduce the light bias level by closing the bilateral slits of the bias source and repeating the measurement. I have reduced to around 0.1 of a sun level. I will now try to switch on the bias light and repeat the scan now with 0.1 sun in addition to the monochromatic probe instant upon the sample. At the end of the scan with 0.1 with sun bias, we have a result which I will save as aSi with 0.1 for sun, we can compare the two spectra by having open windows available, right click, overlay spectra, select the other spectrum you wish to overlay, push it across and hit OK, and we can compare the results in dark to the result in this example with 0.1 of a sun. It may be desired to increase the light bias closer to 1 sun level. That is an experiment that one can perform, and if the spectral measurement returns noise, it is clear that the sample can simply not cope with the heat generated in the 1 sunlight bias.